One of the biggest, most fundamental challenges in all of AI is teaching a computer to truly see. I don't just mean labeling objects in a picture, but to really understand the world from its most basic building block, the pixel. In this explainer, we're going to dive into a really fascinating and honestly super powerful way to do just that.
It's the question, right? It's what's been driving decades of research. I mean, you can show an AI millions, even billions of images, but how do you get it to build a genuine, intuitive feel for the visual world? The kind of understanding that lets it just get things, like shapes and textures and how light works, without being told.
Well, it turns out the answer might not be what you think. It's not as simple as just flooding an AI with complete, perfect pictures of the world. That's one way to do it. But there's another idea, one that's kind of counterintuitive, but maybe, just maybe, a whole lot more powerful.
What if the best way to teach an AI to see isn't to show it everything, but to hide most of the world from it? What if you challenge it to fill in all the blanks, to predict what it can't see based on just the few little clues you give it? This right here, this is the core idea we're going to unpack today.
So this whole filling in the blanks idea is at the very heart of a field we call visual representation learning. The whole point is to teach an AI to create a really useful internal summary of an image that it can then use to do all sorts of other tasks.
And inside this field, there's this really interesting split, almost a philosophical debate. Do you teach the AI to learn high-level, abstract concepts, kind of like how a person thinks, or do you force it to get its hands dirty, to stay grounded in the raw, messy, beautiful reality of the pixels themselves?
This has basically created two competing philosophies, setting up a classic rivalry between two very, very different ways of training an AI. So on one side, you have the reigning champs, models like Dino. We call these latent space methods. They learn by finding these abstract connections and similarities between images. And on the other side, you've got the challenger, pixel space methods, like masked autoencoders, or MAEs. Their goal is way more direct. Just fill in the missing pixels. For a long, long time, that abstract approach, the Dino way, has been the king of the hill. But let's take a closer look at the challenger strategy, because it's actually wonderfully simple and really intuitive. Think of it like trying to solve a digital jigsaw puzzle, where someone's hidden most of the pieces.
And that's pretty much what a masked autoencoder, or MAE, is. It's an AI that's forced to reconstruct the world from really incomplete information. And the crucial part here is that there are no labels, no human telling it what's what. It's just raw visual data.
Okay, so here's how it works. First, we take an image, and we just hide a huge chunk of it, sometimes as much as 75%. All the AI gets to see are these little scattered, visible patches. And its only job is to predict everything that's missing. And I don't mean just guessing a color. It has to reconstruct the entire missing structure from scratch. To fill in the person's silhouette here, it has to understand how light from that monitor is going to create reflections and cast shadows. And by comparing its prediction to the real, original image, it learns. To get it right, it has no choice but to develop this deep, implicit understanding of physics, of geometry, of texture. This means it's not just memorizing pictures, it's learning the fundamental rules of how our world looks. Now, this classic idea was really powerful, but researchers at Metafair and HKU looked at it and thought, can we push this even further? Can we take this underdog approach and turn it into a real champion? So they made 4 really critical upgrades. First, they seriously beefed up the decoder. That's the part of the AI that actually rebuilds the image. Second, they made the puzzle way harder by using bigger, blockier masks. This stops the AI from cheating by just copying nearby pixels. Third, they added more class tokens, which are like little summaries that help the model get the big picture, the overall vibe of the scene, not just the tiny details. And finally, they just scaled the whole thing up, big time. And with those 4 changes, they transformed the standard classic MAE into a brand new, seriously formidable model they called Pixio. It's the same core idea, just bigger, stronger, and trained on a much, much harder test. And when I say they scaled up, I am not kidding. Pixio was trained on a dataset of 2 billion images crawled from the web, using this clever self-curation trick to make sure it focused on the most visually rich and difficult examples. So the stage was set. The training montage was over. The supercharged challenger, Pixio, was ready to step into the ring and go head-to-head with the reigning champion, Dino, across a whole bunch of really tough computer vision tasks. First up, depth estimation. This is all about judging the distance of every single pixel in an image. It's a massive deal for stuff like robotics and 3D understanding. It's how a machine builds a sense of physical space. And on this test, where a lower score is better, Pixio didn't just compete, it smoked the champion. A pretty significant win.
And this wasn't some lucky punch. When they tested it on 3D reconstruction, which is this incredibly hard task of building a 3D model from just a couple of images, the researchers themselves found that Pixio just consistently delivered better results, period.
And this versatility just kept showing up everywhere. Whether it was semantic segmentation, that's assigning a category to every single pixel, or being the visual brain for a robot, where understanding the environment is everything. Pixio just proved to be more effective. The challenger had officially taken the title.
So, what does this all mean for the future of AI? Well, Pixio's success really suggests that maybe, just maybe, we've been a little too quick to jump to these abstract, human-like concepts. Maybe there's still a ton of untapped power waiting for us right there in the raw data itself.
When you boil it all down, this pixel-based approach isn't just simpler and more efficient. It actually forces the AI to learn the fundamental physics of our world, grounded in what it can actually see, with less human bias baked in. It proves that sometimes the most direct, straightforward path is actually the best one.
And that leaves us with this one kind of mind-bending final thought. This entire model learned these incredible skills without ever being told what a door is, or what a reflection is, or a shadow. It learned all of it from scratch, just from the pixels. So, if an AI can develop such a profound understanding just by trying to fill in the blanks, what new patterns, what hidden structures, what parts of reality will it eventually see that are completely invisible to us?